Suppose we can take a 4-node graph. So it consists of 4 vertices and m, the given number of colors. M is equal to 3. So how to find out all possible solutions for this given graph? For a given graph, all the solutions can be represented by using a tree called as state space tree. So here the state space tree can be represented by using a root node. So what are the possible number of colors are there? So there are 3 colors are there. So 3 colors are first color, second color, third color. Suppose we can take a vertex A. What are the possible number of colors we are using for vertex A? So vertex A can be colored with either first color or second color or third color. Okay. So we are using a first color. Okay. For vertex A, we are using either first color or we are using second color or we are using third color. First, for this given problem, what are the optimal solution? What are the solutions? The solution can be represented by using state space tree. Suppose for vertex A, what are the possible number of colors we are used for vertex A? Either first color may be used or the second color may be used or third color may be used. So first color may be used or second color may be used or third color may be used. Suppose for vertex A, we are using the first color. Then what are the possible colors we are used for vertex B? So the remaining colors are either second color or third color. So for vertex B, we are using either second color or third color we are using for vertex B. Suppose for vertex B, we are using the second color. What are the possible colors we are used for vertex C? So for vertex 1, first color is completed. For vertex 2, the second color is completed. So what are the possible colors we are used for vertex C? So the remaining color is 3. Next, which color we are using? Either first color or third color here. For vertex C, what color we are using? Third color we are using. Also first color we are also using. So because A and C are not adjacent, so the first color may be used for vertex C and the remaining color also used for vertex C. So the possible number of colors for vertex C are 1 and 3. For vertex C, so x3 is equal to 1 or 3. Next, suppose for vertex C, we are using the first color, then what is the possible number of colors are used for vertex D? So vertex D is filled with either second color, because B and D are not adjacent, so we are using the same color. Next, the remaining color is third color. So either second color or third color may be used for vertex D. So vertex D is filled with either second color or third color. Next. Next, we can take this path. So all the vertices are completed. All the vertices are filled with color. Vertex A is first color. Vertex B is the second color. Vertex C is first color. Vertex D is second color. So we can take this path. Vertex A is first color. Vertex B is second color. Vertex C is first color. Vertex D is third color, filled with third color. Next, we can take this path. Vertex A is first color. Vertex A is first color. Next, vertex B is second color. Next, vertex C is third color. So what are the possible number of colors we are used for vertex D? So which color we are using? So second color we are using for vertex D because B and D are not adjacent. So one, it is not possible because, so suppose we are using first color, so vertex A and vertex D are adjacent. So these two vertices does not use the same color. Suppose we are using third color, so vertex C and vertex D are adjacent. So these two vertices have the same color. So the constraint is wrong. So then we can go for vertex D is filled with second color. Vertex D is filled with second color. Next, again we have to backtrack to this one. So in this path, vertex A is filled with first color. Vertex B is filled with third color. Next, what are the possible colors we are used for vertex C? So the first color, because A and C are not adjacent. Next, what is the remaining color? That is second color. So either first color or second color may be used for vertex C. So this is x3 is equal to 1 and this is x3 is equal to 2. Next, suppose vertex C is filled with first color. What is the possible number of colors we are used for vertex D? So what is the remaining color? That is second color may be used for vertex 3 and third color may be also used for vertex D because B and D are not adjacent. What is the color we are using for vertex B? The same color can be used for vertex C. So that is third color may be also used for vertex D. So then what is the color we are using? Either second color or third color may be used for vertex D. Next, again we have to backtrack. So C is already filled. Again we have to backtrack D. Suppose we can take this path. Vertex A is filled with first color. Vertex B is filled with the third color. Vertex C is filled with second color. What are the possible number of colors may be used for vertex D? So that is third color may be used for vertex D because B and D are not adjacent. So what is the color we are using for vertex B? The same color can also use it for vertex D. So that is x4 is equal to 3. Okay, again we have to backtrack to C, again we have to backtrack to B, again we have to backtrack to A. So all the paths contains 4 vertices A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. So again we have to backtrack to root node. Next, so we can consider this one. Okay, so the first vertex may be filled with second color. So what are the possible number of colors we are used for vertex D? So the remaining colors 1, 3, because 3 colors are there. So among 3 colors, vertex A is filled with the second color. So what are the remaining colors? That is first color or third color that can be used for vertex B. So vertex B is filled with x2 is equal to 1 or x2 is equal to 3. So vertex B. Suppose vertex B is filled with the first color. What are the possible number of colors we are used for vertex C? So that is the second color can be used for vertex C because A and C are not adjacent. Next, what is the remaining color? That is third color. So either second color or third color are used for vertex C. So that is x3 is equal to 2, x3 is equal to 3. Next, suppose vertex C we are using the second color. What are the possible number of colors we are using for vertex? Vertex A is filled with the second color, vertex B is filled with first color, vertex C is filled with second or third color. Next, what is the possible color we are using for vertex D? That is first color. So this is first color. So this is x4 is equal to 1. Next, suppose we can take this one. Vertex A is filled with the second color. Vertex B is filled with first color. Vertex C is filled with the third color. What is the possible color we are using for vertex D? It is only one. Vertex A is filled with second color. Vertex B is filled with first color. Vertex C is filled with vertex A is filled with the second color. Vertex B is filled with first color. Vertex C is filled with the second color. What are the possible colors we are using for vertex D? 1 and 3. So that is x4 is equal to 3. Now we have to backtrack. Vertex A is filled with second color. Vertex B is filled with first color. Vertex C is filled with third color. What is the possible color we are using for vertex D? It is only 1. Only 1. x4 is equal to 1. Next we go for this part. So vertex A is filled with the second color. Vertex B is filled with the third color. What is the possible color we are used for vertex C? That is 1, 2. For vertex C, 1 or 2. Next, suppose we can take first color for vertex C. What are the possible colors we are using for vertex D? That is only 3. Only 3. Next, suppose, but again we have to backtrack to C, again we have to backtrack to B. Vertex A is filled with the second color, vertex B is filled with the third color, vertex C is filled with the second color. What is the possible color for vertex D? That is 1, 3. And 3. So all the vertices are colored So next we get backtrack to C, backtrack to B, again backtrack to A. Next we can go for third one. So vertex A is filled with third color. So what are the possible colors we are using for vertex B? Either first color or second color for vertex B. First color or second color. Suppose vertex A is filled with third color, vertex B is filled with first color. What are the possible colors we are using? Second color or third color. A and C are not adjacent. We are used the third color. And what is the remaining color? That is second color. C, second color or third color. Suppose we can take the left hand side. So vertex A is filled with third color, vertex B is filled with first color, vertex C is filled with the second color. So what is the color we are using for D? That is only first color. Next, we can backtrack to C, can backtrack to D. Vertex A is filled with third color, vertex B is filled with first color, vertex C is filled with the third color. What is the possible color we are using for vertex D? Either 1, 2. 1, 2. Again, we have to backtrack to C, backtrack to B, backtrack to A. Next, vertex A is filled with third color, vertex B is filled with the second color. What are the possible colors used for vertex C? Either 1, 3. 1, 3. Next, we can take the left hand side path. Vertex A is filled with third color, vertex B is filled with second color, vertex C is filled with first color. What is the possible color we are used? Only 2. Next, we can backtrack to C, backtrack to B. Vertex A is filled with third color, vertex B is filled with second color, vertex C is filled with third color. What is the possible color we are using? That is 1, 2. 1, 2. So in this way, we have to find out all possible solutions for a 4-node graph with M coloring. For a 4-node graph with 3 colorings, 3 colors. State space tree for. So this is the state space tree for a 4-node graph with 3 colorings. How many number of solutions are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 solutions are there. Okay. So each and every solution is represented by x1, x2, x3, x4. Okay. So each and every xi can take either first color, second color or third color. 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 So each xi can take 3 values, either first color, second color or third color. So suppose we can take this path. Okay, vertex A is filled with first color, vertex B is filled with second color, vertex C is filled with first color, vertex D is filled with second color. No 2 adjacent vertices have the same color. This constraint must and should follow while draw the state space tree. Next, what is the time complexity for this graph coloring problem? So is equal to big O of n into m power n. This is the time complexity of the graph coloring problem. Okay. So this is for a given graph with the m colors, how to find out all the solutions using state space tree. So this is the introduction about the graph coloring problem and the example problem on graph coloring. So Thank you for watching this video. If you like this video, please subscribe my channel name Divvela Srinivasa. So please subscribe my channel. Thank you. Hi friends, today I am giving a lecture on algorithm for graph coloring problem. Graph coloring problem is one of the application of backtracking. Backtracking is one of the algorithm design technique. So graph coloring problem is one of the example problem for backtracking. In graph coloring problem, we can take a graph. That graph has n number of vertices. We have to use m number of colors to color all the vertices of the given graph, with the constraint that no two adjacent vertices have the same color. This is the graph coloring problem. Now we go to algorithm for graph coloring problem. Okay. So this algorithm contains two parts. This is the first part and this is the second part. Okay. So algorithm name is M coloring of parameter k. K is the index of what is the next vertex we have to color. Okay. So brace begin, repeat, brace begin. Okay. Generate all assignments for x of k. So here x of k indicates the number of colors we have to use. So there are n number of colors are there. To color n number of vertices, we have to use k number of colors. So that is next value of k. So here we have to calculate which color we have to use for the next vertex. Okay. So whenever this function is called, then it goes to this part, algorithm next value of k. What is the next highest numbered color? We have to color the next vertex in the given graph. So brace begin, repeat, brace begin, x of k is equal to x of k plus 1 mod m plus 1, where m is the m number of colors we have to use to color all the vertices of the given graph. So this formula is used for calculating the next highest numbered color we have to use to color the next vertex in the given graph. So that color number can be assigned to x of k. If x of k is equal to 0, so there are no new colors are found, because m number of colors already used to color n vertices of the given graph. So that if x of k is equal to 0, no such color exists. Okay, then return nothing. Okay, next one. For j is equal to 1 to n, so there are n number of vertices are there starting from 1 to n. So brace begin. Here we have to check if this color is distinct from the adjacent color. Okay, we have to check adjacent vertices have the same color or not by using this condition. If g of k comma j not equal to 0, if g of k comma j is equal to 1, that is k comma j is an edge. G of k comma j equal to 0, here k comma j is not an edge. Okay, here g of k comma j not equal to 0 means, so that is equal to 1. So g of k comma j not equal to 0 means k comma j is an edge. If k comma j is an edge, what is the first vertex? So k. What is the second vertex? J. What is the color we have to use to color the vertex k? That is x of k. What is the color we have to use for coloring the vertex j? That is x of j. Now we have to check same color can be used for both vertices k and j. Okay. So if these two conditions are true, then we go to the break. If one condition is true and another condition is false, so then we are incrementing the j value. Okay. So this procedure is repeated. So these two conditions are used for checking if the distinct vertices have the same color or not. If k comma j is an edge. Okay. If these two conditions are true, then we have to go to the break. If it is break, then go to the next statement after the for loop. If j is equal to n plus 1, then return nothing. Okay. So next until false. Okay. So this algorithm is used for generating the next highest number color. Okay. So then go to the next one. If x of k is equal to 0 means all the vertices are colored with m number of colors. There is no new color is found. So if x of k is equal to 0 means there is no new color is found. So then return nothing. Next, if k equal to n. Okay, all the vertices are colored with m number of colors. So then k equal to n. Okay, then write x of 1 to n. Okay, if n number of vertices are colored with m number of colors, so then this condition is true. If all the vertices are not colored in the given graph, then this condition is false. Okay, if k equal to n means all the vertices in the given graph are colored with m number of colors. Condition true, then write x of 1 to n. So here x of 1 to n means, so x1, x2, x3 up to xn. What is the color we have to use for x1? What is the color we have to use for x2? What is the color we have to use for x3? What is the color we have to use for xn? Xn means nth vertex. X1 means one vertex, first vertex. Okay, what is the color we have to use? That color number can be written if this condition is true. Otherwise, yes, if m number of colors are not used for coloring n vertices of the graph, then m color is k plus 1. Okay, what is the next vertex? Next vertex number we have to color. So here k vertex is completed, then we go for k plus 1th vertex. Okay, so this k plus 1, k plus 2, k plus 3 up to n. If k equal to n, write x of 1 to n. Okay, so then this condition is repeated until we can get the condition is false. Okay, this is the graph coloring algorithm. Okay, this algorithm is used for generating the next highest number algorithm is used for finding all m colorings of a given graph. That graph consists of n number of vertices. Okay. Here this condition is used for checking if k comma j is an edge, so that two vertices in the given edge k comma edge have the same color or not. Okay. If you have the same color, then we go to the break. Okay. So this algorithm is used for finding all m coloring of a given graph. Next, what is the time complexity of graph coloring problem? So big O of n into m power n. So this is the time complexity of graph coloring problem. Time complexity of graph coloring problem. Okay. So thank you for watching this video. If you like this video, please subscribe my channel name. So Divvela Srinivasa, Divvela, so Nivasarao. So Divvela Srinivasa. Thank you.